Can we start now, Jill? Or okay. Okay. Well, welcome everybody to today's Cancer Center Symposium speaker. It's my pleasure to be introducing Dr. Fuyong Xing. Dr. Xing is a relatively new faculty recruit to the Department of Biostats and Informatics. He graduated last year with his PhD in electrical engineering and computer science from the University of Florida. He had the experience of moving twice with his advisor. So if you want to learn all the ins and outs of New Brunswick, New Jersey, Lexington, Kentucky, and Gainesville, Florida, Dr. Xing can tell you all about that. It's impressive how much productive he was while having to move every time. So Dr. Xing's interests are in machine learning, primarily with the application of biomedical images. And even in his short time here, he's started on some very productive collaborations with faculty in pathology, as well as microbiology and immunology. The last thing I'll say is he's been very productive and he's won several Young Investigator Awards in his career. So many of you know about the DREAM Challenges, which Jim Costello is involved with at our campus. These are public competitions where groups are competing quite a bit with, for analyzing data and coming up with the best methods of predictive modeling. And these tend to have cash prizes. So in medical imaging, there's an equivalent competition called MICAI. And I want to say 2 years ago, Dr. Xing was part of the team that won the competition. It turns out the cash prize is not enough for him to retire based on the algorithm. So we're thrilled that he's here. So again, you've probably heard a lot about things like deep learning, machine learning. The big companies all use it. This is actually what Dr. Xing specializes in with application to biomedical images. So with that, I'll let him talk about today's talk, which is learning to quantify and understand biomedical images. Dr. Xing.
Okay, thank you, Debatus. Thank you for everyone for coming. It's my pleasure to share my research work here today, learning to quantify and understand the biomedical images. Today, the topics will mainly focus on how to develop a machine learning technology to understand the biomedical image data. And this is the outline for today's presentation. First, I will briefly introduce the background as well as the motivations of biomedical image computing, which is my research. And then I will discuss the object detection, segmentation, as well as image understanding in details. So, as we know, nowadays we generate tons of image data or what other format data, video, text, or images each day. This is the same thing happen in the medical domain. We generate the images data, no matter what kind of formats, the pathology images or the CT, MRI, or ultrasound image as well. So we have many data generated each day. So what kind of technology we can use to analyze these kind of data sets? This is the biomedical image computing technology, the research field. So for example, for these images, these are breast cancer image data. So from this image, we can see that there are a lot of tumor cells here. So we can say that probably for this image, this patient, they probably have some kind of breast cancer disease. So how can we to extract the useful information from these kind of images or quantify the biomarkers to determine where are the tumor nuclei or tumor cells and what's the state of the tumor? All this kind of information we can calculate based on the biomedical image computing. So this field is kind of to develop automatic algorithms to analyze the biomedical image data. And the goal is to facilitate the new biology, knowledge discovery, or clinical diagnosis, prognosis, or other decision-making support as well. So in biomedical image computing, our job is to develop advanced algorithm or robust algorithm to analyze difficult data sets. Today, we will mainly focus on about the pathology and microscopic image data. So this is the one of the typical pie life in digital pathology. First, we create some tissues from the human body and do some steps of processing. And finally, we can use some kind of the microscopy to get the images. And with this image data, we can do analysis and also do the diagnosis and deliver the reports to the patient or the hospital. Of course, using the computerized methods, we can do this job much efficiently. And this is the architecture we built in our lab for the biomedical image computing. And first, we get the image data. Then we quantify all the items, such as the cells or the nuclei or some other items in the images. Then based on this quantification, we can calculate the representations, how to present the image for the computers. Then we can do the medical diagnosis. Of course, we can send this computation to the cluster or cloud to improve the computation efficiency. And then once we get the results, we can send back to the user for visualization or the interpretation. Of course, we can also store the images as well as the quantification results in the database for other analysis as well. Today, we'll mainly focus on the biomedical image computing part. So which is this part. Before we go to the details of the algorithm design, I would like to provide you two applications of this kind of technology we can use in the diagnosis. The first one is the muscle disease classification. As shown in this figure, right now we have, I think it's 3 recognized types of myositis muscle disease. The DM, PM, and IBM cases. As shown in the right, the figure. From these images, it's not easy to differentiate a different kind of myositis disease. Actually, this kind of disease usually is diagnosed by the pathologist based on the H&E stand slides, such shown in this figure. The pathologist will look at this kind of slides and they try to quantify the cellular morphology changes in these slides and calculate some kind of biomarker and use this biomarker to differentiate different kind of the myositis disease. For example, for these two kind of muscle disease, DM and PM cases, what's the difference between these two kind of the disease? Usually in the DM disease cases, usually the nuclei close to the perimysium region are clustered with each other, as shown in the left figure. And the muscle fiber close to the perimysium region will usually have a smaller area or size than the muscle fiber than in other regions. And all of these observations you cannot see these kind of things in the PM cases. So we can use this kind of the marker or the quantification result to do the differentiation. So in order to quantify all the biomarkers, such as how many the muscle fiber or what kind of the muscle fiber area, we need to quantify all the items in these images. We need to detect the segment, the nuclei, the cells, and as well as the perimysium as well. So obviously, all of this will require the biomedical image computing technology to quantify this kind of the image data. This is one of the applications for the biomedical image computing. Another application will be neuroendocrine tumor disease grading. For example, this is a very bad disease. For this kind of disease, we want to grade which grade stage of the patient. Usually the pathologist will do some biopsy and get the slides showing the right. And then they want to calculate one kind of the biomarker called Ki-67 score. And this is one of the biomarkers saying that we can be used to determine the stage of or the grades of the tumor. If it is less than 3%, it will be low grade. If it is larger than 20%, it will be high grade. So in order to calculate this biomarker, which is defined in this equation, the number of immunopositive tumor cells over the number of total tumor cells. Again, we need to quantify and differentiate all the cells in these images. We need to classify the non-tumor cells, including the lymphocytes as well as the stroma cells. We need to classify the immunopositive and the immunonegative tumor cells as well. So here I give you two applications of the biomedical image computing technology we can use in the clinical practice as well as the medical diagnosis. And of course, for this kind of the image data, we have a lot of challenges. The first one probably will be the background clutter. For these images is the breast cancer in the pathology image data set using the H&E staining. It's not easy to differentiate the nuclei from the background, as you show in these images. And in addition, the intensity inside the objects are very inhomogeneous. So all this will significantly challenging the automatic algorithm we design. Another challenging will be the inter-object evaluations. As we can see, some of the objects or cells will have a very weak object boundaries. And maybe some of them will touch or even partially overlap with each other. In this case, it will present significant challenges for the methods. Actually, this is only 2 small pages we crop from the whole slide scanning image data. For this kind of whole slide scanning, it has a huge dimension, and I think it's billions of image pixels here. It will be very difficult for the pathologists or the doctors to manually count how many objects here or how many cells or nuclei here. Even for the smaller size, the TMA image data has tens of thousands of objects in these images. It will be extremely difficult to manually differentiate which cells are tumor or which are non-tumor. So that's the reason why we need a high throughput biomedical image computing. And the goal is that we would like to teach the computer to learn and see, and later on, the computer will help us to see better. So now we talk about a little bit about the background. Now we are ready to talk about the details of the algorithm design. This is one of the typical pipeline in digital pathology for the diagnosis. We have the image, probably we do some image pre-processing, and then we quantify all the items, the cell counting, detection, segmentation, as well as maybe the tracking as well. Then, based on this quantification, we can calculate the features or representations. And based on this kind of quantified biomarker, we can do the diagnosis. And we'll first talk about the object detection. First, object detection is to detect the objects in the images. Where are the objects in these images? Usually, we want to find the geometric centers of the objects. And of course, there are many algorithms or methods you can use for the object detection. And for example, this is one of the algorithms we developed, I think is 4 years ago, based on the radial symmetric voting algorithm. This is a non-linear based method to detect each item of the objects. Actually, this is the one limitation for the non-linear based method you use for the object detection, because for other data sets, or the image is very different from the one you design. Probably you need to manually update the algorithm or tune the parameters to different kind of data sets. For example, for this image data, the breast cancer or the lung cancer as well, this kind of image data has very different image appearance from the near image data. So probably we need to redesign or carefully tune up the parameters of the algorithm to adapt to different data sets. So probably from here we can ask that, can we learn this kind of processing rules from the images such that it can apply these rules for automatic image processing? That's machine learning based method. Usually in traditional machine learning method for object detection, given the image data, we want to classify each pixels, and this pixel is inside or outside the objects. And in order to train the classifier, you need to quantify the pixels. That's what we mean features in the machine learning terminology. Probably you want to use intensity or some other color or some other features for the quantification, and then train a classifier to the object detection. But there's one potential limitation for this kind of technology, because you need to manually design what kind of features you want to use, or this features is robust to different kind of variations in the images or not. Fortunately, we can use deep neural networks. Deep learning neural network is one kind of the end-to-end model. Given the raw image data, it can directly output the final output, given the labels or the object detection. And all in the middle, the feature design and also the classified training, it will handle by itself. So the problem is that how to design a proper architecture for object detection in this kind of image data. So this is the one of the architecture we designed 2 years ago for the object detection. As usual, we formulate this object detection as a binary classification problem, and based on convolutional neural networks. Here we use 7 layers convolutional neural networks. It's not that deep, but it's compared with the traditional RNN, is already deep enough. We use 2 convolutional, 2 mixed pooling, and then 3 fully connected layers. And the final layer, we only have 2 units because we do binary classification. And after we do 2 convolutional, 2 mixed pooling operations, we found that the feature map is already have a very small size. So we choose to use 3 fully connected layers to learn the more high-level representations for classification. So how to train this model? In order to train this model, we want to minimize the negative local likelihood. And the equation is defined in the top panel. Actually, the likelihood will define using the softmax function is shown in the top right. And y here is a one-hot vector. Only one element will be equal to 1. All the others will be equal to 0. And minimize this equation actually is maximize the probability we assign the correct label to the training data. So after we can do the training, we can minimize this loss function. In order to do the training, we generate millions of patches for model training. And for the positive patch definition, we define this way. If the center pixel of the patches is located in the central region of one real object, then we say it's a positive. Otherwise, it will be negative. In total, we generate about 2.3 million of patches for the model training, and it takes about 2 days using GPU to train this model. And after we train this model, you can deliver this model to the user and then for the object detection in the testing image data. For example, for these images. This image will never see in the training stage. We use the slicing window-based method to detect for each pixel. We make a prediction and how likely this pixel is inside the objects. And then based on the probability method we get, we can find the local maximum as the locations of the targets we want to find. So this is we use the sliding window for the pixel watch prediction, and then we apply this algorithm to the whole disk image data, and then this is the net image data, as well as we also apply to the brain tumor, as well as the breast cancer as well. And we compare with other traditional machine learning-based method. And as we can see, in particular for the breast cancer image data, which is much more challenging, our algorithm can produce much better performance. Here we discuss how to design a deep convolutional neural networks for the object detection for image quantification. And as we remember, we use the slicing window method. Actually, sliding window is covered very slow because it do a lot of repeated computation during the convolution operations. So now we develop another new architecture which is based on deep, fully convolutional neural networks. Actually, the idea is that we replace all the fully connected layers with the convolutional layers and do the upsampling, map the feature map we learn in the middle layer to the space of the input image data. In this case, this network can directly output the feature map which has the same size of the input image. And in this final output image data, the local maximum will directly indicate the location of the targets. And another benefit for this architecture is that it can offset the arbitrary size of images as long as your computer memory can allow discover the large image data sets. So I will not go to the details of the mathematical equation, but I do want to mention that for the loss function we define. Here, as you can see in the labels, in the figures in the bottom left, a lot of pixels are background and then have 0 values. So actually, we're only interested in the central region of the objects. So in order to avoid the model learning bias to this kind of background, we define a weighted mean square error for the model training. And for a little bit more detail about the structure label in the bottom left, this is more detail. In order to train this model, we need to give some kind of supervised information. And this is what we define for the structure label. Given the images, and then also the human annotation ground truth as well, we calculate one kind of the structure label which we call proximity mask, to measure how far of each pixel from the human annotated location in the image data. And then based on this calculation, we can define this is some kind of the structure label to supervise the model to learn. And here for the computation, we normalize it for each value will between 0 or 1, because in the final layer of the neural networks, we will use the sigmoid function. We will require the 0 and 1 values between this range. So actually, for this model, we can use the standard Baker propagation algorithm to train it, and then once do the training, we can apply it to the testing image as well. For this one, for this breast cancer, 1,000 by 1,000, 1,200 by 1,200 is very fast. Using GPU is only a couple of seconds. And this is another example. We want to detect all the items here. So it is very fast. And we also compare this algorithm to other deep learning methods as well, and more details will be in the paper. So as we can see, the performance produced by our method is kind of better than the others. And this is, we talk about how to do the object detection using the deep neural networks and in the pathology image dataset. So after object detection, what's next? Remember that our goal is to do provide support for the medical diagnosis or prognosis. Actually, we want to classify each items in this image. Probably some of them are non-tumor and the other are tumor. And in order to do the classification, we need to quantify each object in these images. Probably you want to measure the shapes or the size or some other features for each item and then do the classification. In order to do the object quantification, you need to segment all of them. This object segmentation will be next topic. So different from the object detection, segmentation will require accurate boundary delineation of all the objects, including those touching cases. So in biomedical image computing, it's very important to preserve the shapes or size when you do the segmentation, because later on, we need to calculate the cellular features for this or for all the objects and then do the classification. Another key point is that we need the algorithm should be scalable to large or high dimension image data, something like this kind of image data sets. So the algorithm should be robust or scalable to this kind of data set. You don't want to wait 1 day or maybe 1 week to get the results. So it should be fast. So here we first talk about the shape preserve object segmentation. As usual, usually there are many algorithms you can use for object segmentation based on the image appearance, the gradient or the intensity or the texture as well. For example, you can use the level set or graph cut methods to do the object segmentation. This is one of for this image we show here, we use a level set to segment each items. As we can see, only based on the image appearance, it's not necessary to guarantee that you can preserve the shapes or size of the objects, in particular for those touching cases or those that have a very weak object boundaries. So, on the other hand, the subprime modeling, it can preserve this high-level information. So our idea is that we would like to use the subprime modeling to constrain the image appearance model to do the accurate object segmentation. So this is the whole framework. This framework will connect two modules. The first one is the image appearance model, which we develop a novel, repulsive deformable model. And for the subprime modeling, we develop a sparsity-based shape decision learning. And given the initialization, which is provided by the deep neural networks that we talked about a few minutes ago, and given these locations, we will run this model to alternatively to run a contour deformation and shape inference, and repeat this procedure until the contour move to real object boundaries. And now we will go to the stage, each step in details. Actually, the whole framework will including training and testing stage. And we already discussed about the deep neural networks learning, then we can talk about the shape distance learning right now. Suppose that we have a lot of training data. I mean, it's shown in the left figure. We have a pixel-wise. We have the pixel-wise contour annotation for all the items in these images. Do we need to use all of them for the shift inference in the testing stage? Probably this is not a good idea, because in that case, you need to search in all the entire database for the shift prime modeling. In that case, it will be kind of slow and time-consuming. Our idea is that we only need to select only a few of them to represent the entire database. This is a additional learning problem. And the goal is that we want to learn a compared shift dictionary, such that for any testing objects, it can represent it using this learner dictionary. And this is the optimization problem we formula. Here we want to minimize the integrated square errors, and we also add one local regularization terms here as well, because we want to guarantee the local smooth, which means for the similar cases, their representations should be similar. So actually, this model is very complex. It has a lot of unknown parameters. It's not easy to solve this problem. And then we solve this one using in an alternative way. We update one with the other fix and repeat this procedure until the algorithm converges. For example, when we update the dictionary, actually we assume all the other fix and then update dictionary, and then keep the dictionary fix and update all the other parameters. And we repeat this procedure until the algorithm converges. Usually it will take about 150 iterations where the algorithm will converge. After the converge, then we can get a shape dictionary, which can be used in the testing stage. As we mentioned before, in the training stage, in the testing stage, we do once shape inference and then once contour deformation. For the shape inference, we can solve this optimization problem, do the sparse reconstruction, and then for the shape inference, based on the dictionary we learn. Then for the contour deformation, to move the contours to the real object boundaries, we develop a new repulsive model, which we call repulsive Bruce-Snake model. And the idea is that this model is an active contour model. Given the initial contours, it will automatically move all the contours towards the real object boundaries by minimizing the energies defined in these two equations. And our contribution is that we introduce a new term here. We want to prevent the neighboring contours from crossing or merging into a single one. As we can see in the images, all the cells touch with each other, and the contours will not cross or merge into a single one based on the newly introduced term. So this model is very effective for the segment discovery of the image data. So this is the image shape preserve object segmentation we developed for the image data. So how about big image data? As we mentioned, if the image has a very large dimension, then has millions or billions of pixels. Remember that in the previous slide, we mentioned that we would like to do the contour deformation. And actually, this contour deformation dominates the running time when you do during the testing stage. Compared with the shape inference, it takes a much higher time cost. And as shown in this figure, the reason is that we need to calculate or solve the Euler-Lagrange equation for each item within each iteration. So this is very time consuming. So these two equations it takes a lot of time. So we want to find a way to avoid this computationally expensive method. Actually, based on our observation, we can find that actually we can group the similar cases into the same cluster. And in the same cluster, we use alpha transform to approximate the contour involvement. In this case, it will significantly reduce the running time, because compared with solving the complex Euler-Lagrange equation alpha transform matrix computation is much cheaper. So we can use that to reduce the running time, but there's still one more issue here, because how can we dynamically update the membership for each item or each object in this in the testing stage, and how do we determine which this object belongs to which cluster? So actually here we develop a scalable manifold learning algorithm to do update the membership update. As usual, we learn dictionary similar what we did in the previous slides, and then this dictionary will have multiple corresponding to multiple suppliers, and one subgroup will correspond to one kind of supplier, and then in the testing stage, we don't need to learn the dictionary again. We just do the sparse encoding. For example, for these two images, for these two objects, obviously they are very different. The shapes are very different. Actually, when you do the sparse encoding, actually they use very different dictionary bases to the reconstruction. And this is provided very important information for us. We can use this kind of information to determine that which cluster this object belongs to. So by calculating the maximum non-zero elements in the sparse codes. So this is the three steps of the scalable manifold learning algorithm we developed 2 years ago. And the entire algorithm we will show in the table in the right. We will not go to the details yet. And in summary, for this algorithm is that given the new image data, we do the grouping, and then similar cases were in the same cluster, and within the same cluster, we only randomly pick one to do the contour deformation by solving the Euler-Lagrange equation. And then for all the other objects in the same group, we just use alpha transform to the approximation. Then we update the cluster membership and also do the shape inference as well. And finally, we update the alpha transform matrix and then repeat this procedure until the algorithm converges, which will mean that the contour will move to the real object boundaries. And we apply this algorithm to the whole disk image data set. And this is one example. This is another example for the image data. We also apply it to the brain tumor, breast cancer as well. We compare many other compared with some other algorithms as well, the graph cards, level set, as well as the watershed as well. And then in all the three card data sets, the proposed method can produce the best performance. So here we talk about how to do the object detection, efficient object detection, segmentation, and especially for the shape preserved object segmentation. Actually, we developed a lot of other algorithms to make more contribution to the biomedical image computing. And due to the limited time, we will not go to details of each of them here. For example, how to train a model using limited training data and for the object segmentation, and how to do develop robust algorithm for the image segmentation as well as fast object detection as well. For the finally, we also have the large-scale image retrieval for lung breast cancer as well. So all the detail you can find in the paper. So here I will quickly show you the results of the image quantification. For example, for this one, this is the muscle image data. We quantify all of them and classify all the items as well. And some of them are disease fiber, and the other is not disease. And this is the lung cancer as well. We quantify all these items and detection segmentation as well. Actually, all the algorithms that we develop have one goal. We would like to provide support for the diagnosis or prognosis. So actually, in the clinical practice, the pathologists or the doctors, they are more interested in this kind of question. For these images, does the patient have disease or not? And where are the tumor cells? And how many tumor cells here? And what is the KICT score? So in addition to object segmentation, we still need to do object classification to classify all the items here. And this is one of the architecture we developed for the automatic KICT scoring in the image data. And based on the image quantification, we do such as the detection, segmentation, as well as the classification, we can calculate the features, the certain features, the intensity or the texture as well, and then train a classifier, SVM or random forest or other classifier. Then you classify each object in these images for the automatic KI safety scoring. And here I'll quickly show you some results here. As we can see, thousands of the objects will correctly detect, segment, and classify. And actually, this is a multi-stage algorithm for the KI safety scoring. Actually, right now, we are one ongoing project that we want to use one single stage KI safety scoring, which means that we want to do all these tasks at once. So in this case, it will reduce the errors because the final stage will not heavily rely on the detection segmentation. In particular, we will bypass the segmentation, the stage, in the current stage. So this is one application. Based on the image quantification result, how can we do the one step forward for the understand the images? And another application is the myositis classification or diagnosis. Based on the image quantification, we can calculate the features, such as the distribution of the nuclei, or also the muscle fiber, the size of the muscle fiber, and the number of the nuclei, as well as muscle fiber as well. And then, based on these features or representations, then we can train a model. Here, we train a random forest model for the disease classification, and to classify the myositis DM, PM, or IBM. This is one of the applications. Another application is the lung cancer survival analysis. This is the last application we'll talk about today. Based on the image quantifications, we do, such as the detection segmentation, we can quantify all the biomarkers, such as the cellular features, the perimeters, the area, intensity, or the size, all kinds of features you can calculate. And then, based on these features, you can calculate the mean standard deviation or other statistics features, as well as the histogram, to concatenate all these features into a final single feature vector to represent the entire image data for each patient. Then we can do the survival analysis. Based on, as we see in these two figures, there are a significant difference between these two groups, the low and high risk groups, which means that the image representation we deliver is very effective in this task. And this project is collaborated with the Department of Statistics in my previous university. And our contribution is that we quantify the images and then deliver the image representations as well. And I think this is all the applications for today. And here I will list some of our publications if you are interested in our research to do how to use the machine learning, including the deep learning technology to quantify and understand the biomedical image data. You can find more details on my website. I think that's all for today. Thanks.
Thank you. Questions for Fuyong? Yes, go ahead.
Thank you for your presentation. So there's some on we can use like aerial. I mean, there's. Are you familiar with it?
Yes,
Scan the images.
I know that.
You can also teach. How does your compare to that? And could you also comment if it is really available?
Okay. Yes, sure. Actually, all the algorithm here, we develop and design our algorithm by ourselves, and then we write our own codes. And then most of them we already publish online in the codes, but we don't, because we are more focused on the algorithm design and the computing part. We will not provide the kind of friendly user interface. As you mentioned, for the Appeal Rail, it's a commercial software. They provide very friendly user interface for the non-machine learning researcher can use. But usually for this kind of complex image data, their algorithm will fail in most of the cases. Actually, we compare our algorithm with the appeal in the KI settlement score. In our paper, I think the appeal is not do the good job there in the counting, especially for the classification as well. And also, I also collaborate, because I collaborate, all the projects I collaborate with the pathologists and the doctors in the hospital, actually based on their opinions. Appeal, they can do some work, but it's for most of the time, they have the difficult cases. They have a heavy background clutter and the intensity inhomogeneous. It's not easy for them to get work, or it will require a lot of time for you to tune the parameters or to set up a different kind of the parameter value on. And this is non-trivial for those researchers that don't have the machine learning or computer vision background. They don't know how to tune the parameters, or maybe for this data set they can work well. For choosing another data set, it's not easy to tune these parameters. But based on machine learning, it can learn the rules automatically from the image data. So this is one of the big advances for machine learning. And one step forward for the deep learning, you don't need to manually design the features as well, because for traditional machine learning, you also need to design what kind of features or representations you want to use. And this is a non-trivial task. Actually, feature engineering is a subfield in machine learning. A lot of people working on, or in computer vision, a lot of people working on how to design robust features to do the classification, detection, segmentation. This is non-trivial. But for deep learning, you just giving the raw image data and the final output, you will learn the features and learn the classifier as well. For you, I think this is also probably one of the reasons deep learning is very popular nowadays.
Other questions for Fuyong? Actually, maybe a question for you. Could you say a little bit about you mentioned this stuff is kind of computationally intense. Mm-hmm. Could you say a little bit about sort of the GPU machine you have and sort of
yes,
how it helps with your modeling?
Okay. Actually, for the deep learning model here, we have one GPU machine specifically designed for the deep learning. As you know, deep learning model is a huge model, has millions or even billions of parameters you need to train, you need to learn. So for the standard machine using CPU, no matter what kind of the powerful CPU you have, you will not compete with the GPU. So we have one machine, have 4 GPU for the model learning. And I think that there's another computing resource that probably you can use is for using the Google Cloud. I think last week or 2 weeks ago, Google just released their TPU, cloud TPU for the deep learning model training. But unfortunately, it's non-free. It's $6.5 per hour. So if you guys interested, you can try use the Google Cloud to train your deep neural networks model. And I do want to mention that compared with the CPU training, using GPU will much faster. Usually in our model, I mentioned that for the 2.3 million of the image pairs for the model training, it takes about a couple of days. But if we use your CPU or standard machine to train it, probably it will take months or at least a couple of weeks to get the model to train. Thank you. Oh. I'll just delete it.